Hello and welcome to my second video lecture for class 11 in atomic structure. The first one was, as you remember, those who have seen, was on Planck's quantum theory. Today we shall be discussing on atomic spectroscopy. Now the term spectroscopy is so very vast that a beginner like you need its proper concept. I assure you that I will be restricting my discussion to the fundamentals where I think the possibility of meeting any confusion will not be there. Now, let us talk what is emission spectrum. Spectrum are of many types. First, let us know what is an emission spectrum. Let me read out these lines which I have prepared for you. It is good for understanding. When a certain source is emitting light or any other radiations, electromagnetic radiations, and we pass these radiations through a prism or a super prism, that is a diffraction grating, the radiations get dispersed. Previously it was a bundle of radiation mixed, and when it is passed through a prism, which is a separator, it is dispersed to form an orderly arrangement of radiations or colors. If it is visible radiation, then we say colors. If it is invisible radiations, we say radiation, simply radiation. Radiation is a common term. So these forms, the dispersion of these radiations will form an orderly arrangement of these radiations from the lowest wavelength at the bottom to the highest wavelength at the top. This pattern, this spread of colors or spread of the radiations from the lowest wavelength to the highest wavelength, from the highest frequency to the lowest frequency. As you know, frequency and wavelength, they are inversely related to each other. So this spread that will be recorded in a screen or in a photographic plate. If it is visible, then you can arrest them on a screen. You can see it in your eyes. But if it is not visible, then you have to take the help of a photographic plate, and then you take the picture of that spread, and you can know this pattern of this spread of radiations. Previously it was a bundle of radiations mixed together. When it passes through a prism, it separates into a smoothly increasing wavelength from bottom to top. So this pattern is called as an emission spectrum, more correctly an emission spectrum, but more correctly an emission spectrum. Now this is the solar spectrum. The source is sun, which is emitting radiations, and so many types of radiations, and we are only taking the white light from sun. It was white, and when it is passed through a prism, then it produces a continuous pattern of colors. Vibgeo, violet to red. This is the smallest wavelength, and this is the longest wavelength, the red. So this spread, when this is captured in a screen, on a screen or on a photographic plate, then you see the colors continuously, one color, then the other color, then the third color, and so on. There is no gap, no discontinuity in the entire spread of colors. So this is the emission spectrum of the sunlight, the white sunlight. It was white, it mixed, but now spread into the individual colors. Each color contains infinite number of radiations. Now let's see the different types of emission spectrum. It can be continuous or band spectrum, or it can be discontinuous or line spectrum. Now, just now we saw solar spectrum. That is a continuous spectrum. No discontinuity from start to finish. There is no gap. Every space is filled with some color or the other. Similarly, we shall be discussing later in details. The hot black body also produces radiations in the IR as well as in visible region continuously. You get a continuous pattern. And you remember in earlier times you were getting an electric bulb that is called the incandescent electric bulbs using filaments. Those bulbs are no longer in use. They are replaced by CFL, LED. So you must have seen earlier times in our childhood times we were using, or maybe 10 years before when these LED bulbs were not popular, we were using those incandescent bulbs, electric bulbs. So the yellow light that it produces, when you pass that yellow light through a prism, you get also a continuous spread of color. Not exactly Vibgio, but a continuous spread of color. So such spectrum, the plural is spectra. Such spectra are called continuous or band spectrum. But contrary to that, we have another kind called the discontinuous or line spectrum. For example, you take sodium vapor in a flame. Sodium vapor in a flame, you will find the sodium will emit golden yellow light. So when you take that golden yellow light and pass through a prism and put a screen, you will find only two lines, well separated two lines in the yellow region. Those are called the D1 and D2 lines of sodium. One at 5890 angstrom, the other one at 5896 angstrom. Only two lines. So this is called a line spectrum or discontinuous spectrum because there is no continuity between the lines. And another example is hydrogen spectrum. We shall see when hydrogen gas will be given energy by electrical method, and you will find it will radiate, it will produce a reddish white light. When hydrogen produces that reddish white light and we analyze that reddish white light through a prism, you will find there are several spectral lines. In the visible region you find one, in the orange region the other, in the blue region third, in the indigo region, and a selected few lines well separated from each other. These are called the line spectrum of hydrogen. Similarly, every element produces a unique and distinct emission spectrum. When it is heated, energized, it produces light, and we analyze that light, and you find the spectrum on a screen or in a photographic plate. You find they are all individually distinct. They don't match with any other elements spectrum. So all the elements, they have discontinuous or line spectrum. The examples of continuous or band spectrum is limited. The very classic example of solar spectrum containing Vibgio and blackbody radiation is another example, and the erstwhile, the primitive electric wall containing filament, that the light produced by that will also produce continuous or band spectrum. You have a look once again the solar spectrum, which is an emission spectrum because sun is emitting light, and you are getting the spectrum when some source is emitting radiations. That is not only emission spectrum but also continuous Vibgio. But on the other hand, if take hydrogen gas in a discharge tube and subject it to very high voltage and low pressure, it will, at certain conditions, it will produce a reddish white light. Unfortunately, in this diagram it is white, but it is reddish white light. And when you pass that light through prism, it will be separated into individual radiations. One at the orange or red region, the second one is at the blue region, and the third one is at the indigo region, and the fourth, fifth, and in the violet region. So a few distinct lines, for example 6 lines, you will find in the visible region. So when you put it in a photographic plate or in a screen, you will find only few distinct lines. The orange region one line, and blue region, indigo region, violet region is not visible. So a few but unique lines, fixed unique lines for a hydrogen element. This is called the famous Balmer series of hydrogen spectrum. We'll talk about the Balmer series later on, but this is an example of a discontinuous spectrum, like the D1 and D2 spectrum for sodium. Now let us formally talk about what is atomic spectroscopy, and that too emission atomic spectroscopy. Let me read out, and time to time I will explain. All elements are first vaporized into the vapor form. Those which are intrinsically gases at room temperature, it's okay. But the liquid elements, the solid elements, the metals and other solid elements, they have to be vaporized first. At high temperature and low pressure, they will be vaporized into the vapor phase, and they have to be atomized. If it is a diatomic or a polyatomic molecule like H2, O2, N2 or P4, S8, they have to be chopped off into atoms. So they have to be atomized. Not only vaporized, but have to be atomized. By using either heat in a flame, or by using high voltage, that is an electric arc, or any other method. So many advanced methods have been the case nowadays to produce atomic elements in the vapor phase. We'll not talk the details about that now. Then, as you know, the elements, the atom, they have electrons in different cells, K, L, M, K, L, M, N, and so on. You have studied in your lower levels that each atom has different cells or electronic levels where the electrons are there. Now the electrons present in the valence cell, the last cell, that is called the ground state, get excited, get promoted to different higher energy states. Those are called the excited states, by absorbing the different amounts of energy from that energy source. When the electrons from the excited state, they return back, because they can't continue to remain in the excited state or higher energy levels indefinitely. After a very short time, they have to return back to the ground states. When the electrons in different atoms, they return back to different lower energy levels, they emit radiations. As you know, when the electrons are excited from the lower level to higher level, they absorb energy, and when the electrons are de-excited, they return back from the higher levels to the lower levels, they emit radiations. So they emit different radiations. When these radiations are dispersed through a prism, we get the line spectrum, and that is the emission spectrum of the element, because the element is emitting radiations, emitting light, and we are analyzing through a prism to see the spectrum, the sprayed. And definitely we will be getting line spectrum. As I have already told you, all the elements, they have their characteristic lines to emit. We'll talk about the details why not continuously they are emitting. They are emitting certain selected radiations which are giving selected lines to characterize that particular element in a very unique manner. So we'll discuss that later. So we get the line emission spectrum of the element. That when the electrons in different atoms are returning from the higher levels to different lower levels, they emit different energy radiations, and for each energy radiations you have one line, one frequency or one wavelength. That is one line. Elements always produce line spectrum. Each element absorb in its characteristic frequencies, and when they return back, they also emit the same characteristic energies. Now we are taking the spectrum when the element is emitting radiations, where that is why it is called the emission spectrum. And since the emissions are distinct few selected lines, selected frequencies, then that emission spectrum we call it line or discontinuous spectrum, not like the solar spectrum which contains infinite number of radiations. So emission spectrum is otherwise called the hot spectrum because the spectrum is taken when the element is hot. That means when it is subjected to energy. It is first absorbing energy, then it is emitting energy, and we are taking the picture, taking the photograph while it is emitting radiation. So in the hot stage we are taking the spectrum. That is why emission spectrum is often called the hot spectrum of an element. The spectrum of an element is called its fingerprint to identify that particular element and distinguish it from others. You know, just like each one of us, even the twin brothers and sisters, they do not have the identical fingerprint. The fingerprint is different for the two twin brothers and sisters. So you can distinguish who is who but just by matching the fingerprint. Similarly, each element has its own unique uh, spectrum, and therefore the spectrum of an element is called the fingerprint of the element, which distinguishes it from others. Each element gives a fixed number of well separated or discrete lines which do not match with the spectrum of any other element. The yellow light emitted by sodium vapor gives only two lines, D1 and D2 in the yellow region. Similarly, the potassium vapor gives violet light, which forms a series of colored lines. Now have a look, the D1 and D2 line formed by the yellow light produced from the sodium vapor in a flame. That we have already discussed, D1 and D2 lines. These distinct two lines with a gap in between. There is nothing to the right, nothing to the left. In between there is also a gap. This is the discontinuous or the line spectrum. Now here I have shown you 5 elements: titanium, strontium, manganese, copper, beryllium, each of which they produce characteristic unique line spectrum which doesn't match with anybody. Beryllium, copper, they have distinctly different line spectrum. And this one is the spectrum of an unknown element. I give you. You match with these five spectra and tell me, is it any element of these belonging to these 5? Does it match with any other known element? Yes. If you see very carefully, you'll find the spectrum of an unknown element matches with strontium. Have a look. These two red and these 3, this one. So exactly it matches with strontium spectrum. So the unknown element is undoubtedly strontium. So by matching the spectrum of an unknown element with the literature data available for all elements, you can identify the element. Now we talked so much about emission spectrum, when an element or any source is emitting radiations and we are analyzing through a prism. Similarly, when an element is absorbing radiations, we can take the spectrum. When the element is absorbing radiation, we can also take the spectrum and identify that element. But for that, we have to take the help of a light which produces continuous spectrum. Now let us read these lines step by step. Absorption atomic spectroscopy. This is also called the cold spectrum. Unlike the hot spectrum in the emission mode, in the absorption mode, this spectrum is called the cold spectrum. It always gives line spectrum. We shall see very soon what are the nature of these lines. Are the real lines or the false lines? We'll talk about that. When a light which can produce continuous spectrum, such as sunlight or light from an incandescent bulb, that filament bulb, that sort of light containing a mixture of radiations which can give a continuous pattern, such light is allowed to pass through the gaseous atoms of an element in the cold state, not heated, not electrically energized, in the cold state. Then the electrons will absorb. Electrons are in their ground state. When they are cold, they are in their ground state. When they will absorb specific radiations characteristic of that particular element, and they will leave the rest of the continuous radiations, they will leave the remaining and only absorb a selected few radiation, selected monochromatic radiations of having different frequencies characteristic of that particular element. The same radiations which they emit during emission mode, the same radiations now they will selectively eat away from a bundle of radiations, a mixture of radiations coming from either sunlight or a continuous light source from an electric ball. So when the residual light on the other side, after being absorbed by the atoms, when you analyze the residual light in the other side by dispersing that light in a prism, we get the absorption spectrum of the element. That means we get all the same continuous pattern, but those lines will be missing. Have a look. You have a look. This is a bulb, an electric bulb which produces continuous pattern, continuous spectrum. And this is an emission spectrum of a particular element which is in the hot state, and you are emitting, this element is emitting light, and you are analyzing it, and you are putting it in a screen. You are finding these fixed lines on a dark background. You are getting these colored lines. This is the emission spectrum of this particular element. That is the hot spectrum, the emission spectrum. But if you take the same gas element in the gaseous state but in the cold state and take the help of the light produced by either sunlight or a electric bulb, if you pass the sunlight or the continuous light containing all infinite radiations through the atoms of the elements in the cold state, in the ground state, the electrons will absorb and will be promoted to the higher energy levels. And by the time they go, the sunlight or the bulb, light from the bulb will pass through the atoms, come to the other side, and when you analyze that light through a prism, you will find the same pattern as you have found here, but these positions will be missing. These are called the dark lines. The same lines which appeared colored in the emission spectrum, they will be appearing dark because there is nothing, no color. So looking to this pattern of missing lines or the dark lines in a continuous patch or continuous pattern of the original sunlight or the light from the incandescent bulb, which you took to find the absorption spectrum of the element, you will find these missing lines constitute the absorption spectrum of that element. So the information is same. The element is identified either in the emission mode, producing some distinct colored lines, or in the absorption mode. Now the cold state, the atoms have absorbed. We are not waiting till the electrons they return back to the ground state to find its emission spectrum. The light travels in such fast speed that it goes to the other side, promoting the electrons to the higher level, and the same light which was produced from sun or from an electric bulb immediately comes to the other side, leaving behind the selected monochromatic radiations there in the cold gaseous atoms. And when you analyze that sunlight devoid of those selected radiations, you will find the entire spectrum as you found in the continuous spectrum, um, but there will be absence of these particular lines. So looking to these missing lines or the dark lines, you can identify the element. The same, the emission spectrum of any element and its absorption spectrum gives the same information. Here the colored lines, here the missing lines. But this missing lines is discontinuous. We are not talking about the colored background. That we have to take the help of a source. But the absorption spectrum of the element is not the background, the colored background, but the missing lines, the dark lines. I think we have discussed quite a lot about the difference between the emission spectrum and the absorption spectrum. Showing the same thing, this is the solar emission spectrum, sunlight emission spectrum. VIBGYOR is a band spectrum or continuous spectrum. And here the hydrogen element, this is the emission spectrum, which is also a discontinuous, also I should not have used, which is a discontinuous spectrum containing few discrete lines. And this is the same hydrogen absorption spectrum, where it contains VIBGYOR, but these lines are missing. So these missing lines constitute the absorption spectrum of hydrogen. So the two spectra give the same information. This will talk about that the unknown element is hydrogen. This will talk about the unknown element is hydrogen, because the exact frequency they will match. Although this is colored, but this is missing lines or the dark lines, but the frequency will match, the wavelength will match, this will match, this will match, and so on. To repeat once again, to put you in your brain that this is the hydrogen's emission spectrum on a dark background, you have selected color lines, and this is in the background of VIBGYOR, you have the missing lines at the same positions. This is the spectrum of helium. This is the helium's emission spectrum containing so many discrete lines at different regions of VIBGYOR. And here this is the absorption spectrum of the same helium. In the background of VIBGYOR, you are getting these lines missing or dark. But here is a mistake in the picture. This would have been a dark line, but unfortunately this is a mistake in the picture. This is a dark line, missing line. This is the spectrum of helium. Then let us talk something about hydrogen spectra. Specifically, we talk little more about hydrogen spectra. Although the mathematical implications of hydrogen spectra will be taken up in our subsequent video lecture, that is on about Bohr's theory of atom. But we can have a concept of hydrogen spectra. Now, when hydrogen gas is subjected to high voltage at a very low pressure in a discharge tube, as we saw before a few slides, at a particular set of conditions, it emits a reddish white light. This reddish white light, when analyzed through a prism, gives several series of spectral lines, not only one series, several series of spectral lines. These collectively are called hydrogen spectra. These are the different series. One is the Lyman series that falls in the ultraviolet region. The Balmer series, about which we were discussing before few minutes, before few seconds, this falls in the visible region. We can have a look on a screen or also on a photographic plate. Then the Paschen series that falls in the IR region. The Brackett series also in the IR region. You know, the IR region is very vast. Could you remind me what is the range of IR radiations? It's a vast range. I remind you, it is from 7,600 angstrom to 6 into 10 to the power 6 angstrom. It's a vast range. So Brackett series also falls in the IR region. The Pfund series, P will remain silent in its pronunciation. The Pfund series will also fall in the IR region. The Humphreys series also will fall in the IR region. All these four series will fall in the IR region. Balmer falls in the visible. The first person who discovered the hydrogen spectrum is the Balmer. Then the Lyman series falls in the UV region. We'll talk the details in our later program. And this is the Balmer series that we have already shown. We have already seen that there are few discrete lines in the visible. You will find 6 lines, and you find there is a pattern. There is a very typical pattern. The gaps in between two successive lines, they go on decreasing as you move towards lower wavelength region. So this is the first line is in at 656.3 nanometer or 6563 angstrom. And that line and the second line in the blue region, unfortunately it is shown a little greenish, but it should appear in the blue region, as we shall see later in our calculation. This is not the exact picture. I have cut pasted this from Google source. I thank to Google for rendering infinite number of such pictures. There might be some error in the picture. Yes, it is an error. So this is the blue line at 4861 angstrom. The third line is at the indigo region, 4340 angstrom. And you find the gaps, successive gaps are being reduced. This gap is so large, and the second gap is much reduced, and the third gap is still more reduced. And after a few lines, 3 or 4 lines, then the gap becomes so small, then the subsequent lines, they merge onto one another. They merge onto one another, they collapse onto one another, they bury onto one another to form a thin band here. We shall see it later in a clear picture. That thin band of converging lines, this is called continuum. So this is a pattern that is found in every series. Balmer, Lyman, in all series, this is the same pattern, that the successive gaps between the lines, they go on decreasing very, very drastically, and after a few lines, they merge into one another to form a thin band called continuum. Now, let's see what is the cause of showing this emission spectrum, the emission line spectrum. This is once again, we are talking about the emission line spectrum of hydrogen. Now, when you put hydrogen atoms in a particular discharge tube, put it under high voltage electric arc, then the atoms get all types of energy. You know, a sample contains hundreds and thousands of atoms, not merely a single atom. Thousands and thousands of atoms are there. Now, when they absorb energy, all the electrons previously are there in their ground state, that is in the first cell, the K cell, the first cell. This is the nucleus, this is the first cell. They have already absorbed energy of different values. In some atom, the electron has excited from the ground state to the second cell. In some other atom, from the ground state to the third cell. In some other atom, it is from the first cell to the fourth cell, and in some other first to fifth, first to sixth, first to seventh. So you find all different varieties of excited atoms. Within a twinkling of an eye, different energy values, energy radiations will be absorbed by the different hydrogen atoms to go from the ground state to the different higher energy states. Now, after some time, the electrons have to return back. There is no way out. There is a fixed time which an electron can spend in an excited state. It has to return back. So when they return back from different higher energy levels to different lower energy levels, they emit out different varieties of energies with different frequencies and different wavelengths. For example, in the Balmer series about which we were discussing, these lines involve the transition of electron from different excited hydrogen atoms from different higher levels to the same terminating second cell. This terminating cell is fixed, second cell. So the electron which is transiting or transitioning from the third cell to the second cell, that gives you the first line of the Balmer series, that is the orange line, 6560 angstrom. Third to second, this transition will give you a particular energy radiation, that is 6560 angstrom, belonging to the orange region. This second line is due to the transition of electron in another excited hydrogen atom from the fourth level to the same second level. The third line from the fifth level to the same second level, and the next line is from the next higher level to the same second level. Therefore, Balmer, before Bohr could give his theory and his mathematical inputs, he propounded, he gave an empirical equation by using which you can get the exact matching of the different lines. He gave this equation to get the different lines of the Balmer series, his own series, that is nu is equal to, the frequency of each line is equal to 3.29 into 10 to the power 15 second inverse into 1 by 2 square minus 1 by x square. This 2 is fixed. That is the terminating cell. They will come, all of the electrons in different atoms will come to the same second cell. The terminating cell is fixed too. And the higher cells are variable. X can be 3, 4, 5. If it is 3, then it is the first line. If it is 4, the second line. 5, third line. 6, subsequent line, and so on. And you find later when we study Bohr's theory, the energy gaps between these lines become so less that their frequencies, their wavelengths, they will be coming very close to each other, so that they merge, the lines they merge, and you cannot see the difference or the gap between them. They will collapse, they will merge to form a thin band. Now, the Lyman series are due to the transition of electrons in different hydrogen atoms from different higher energy levels to the same terminating ground state, that is the lower state, that is the ground state, that is the first cell. So the transition from the second cell to the first cell will give you the first line of the Lyman series. From the third cell to the first cell will give rise to the second line, and from the fourth cell to the first cell will give rise to the third line, and so on. So all these transitions, all these radiations will fall in the ultraviolet region, which are not visible. You have to take the help of a photographic plate to record these lines. Similarly, the Paschen series are due to the transition of electrons in different hydrogen atoms from different higher levels to the same terminating third cell. From fourth to third will give you the first line in 18,750 angstrom. This is a nanometer. I am changing it to angstrom. The third line is due to the transition from the fifth cell to the third cell. Third is the constant terminating cell. Then the next line is from the sixth cell to the third cell, and so on. So this is a very interesting observation, that hydrogen spectra is not only one restricted to Balmer series in the visible region, but on careful analysis we could find, and different scientists could find, the similar type of lines. The pattern is same, but in different locations, different positions in the electromagnetic spectrum. Now, I show you the 3 series only. It is so long that I cannot show you all the 6 different series. That is 1, 2, 3, 4, 5, 6. Only I have shown you the 3 series here. This is the Lyman series, which has a very little spread, very compact, but the pattern you find the same. The gaps are more in the beginning. As you go towards more and more left to the lower wavelength region, you find the gaps is reduced very drastically, and after a few lines they merge into one another to form a thin band beyond which it doesn't move. There is no more lines. It ends there at this continuum. This is called a continuum, but the lines are well separated. You can see distinct lines. Now the cause of these, more about the discussion on this will be done in Bohr's theory. Just wait for the next video. Then the Balmer series is in the visible region, and it is little more spread out, but the pattern is same. The gaps are reduced and it forms a continuum extending to the ultraviolet region. 6 lines they appear in the visible region, and others they appear in the ultraviolet, not in the screen but in the photographic plate. These are colored. Red is not all are red. It's just red is just a picture. It's not the real lines, colored lines. And these are not red. These are colorless. These are visible invisible radiations, ultraviolet. They have to be pictured in a photographic plate, the UV sensitive photographic plate. So it's not colored. Similarly, the third is in the IR region, infrared region, and the first line of the Paschen series is due to the transition from can you tell me from which cell to which cell? Yes, fourth cell to the third cell, where the terminating cell is 3, here the terminating cell is 2, here the terminating cell is 1. It falls, we shall calculate later on that the energy values will fall in the IR region. So this is the second line and third line. It is a Paschen series, a little more widened, but the pattern is same. Gaps are reduced very drastically, and after a few lines they merge into one another. They don't move beyond that and to form a thin band called continuum. This is called these are called continuum. These last these last these last this thin band, this is called continuum. The last, where it doesn't progress beyond that to the left, it ends there. That is a thin band. That doesn't say that the nature of the spectrum is a band spectrum. It is discontinuous. Largely it contains unique, well separated discrete lines. Lyman series, you can also have a similar equation, but these equations were not given by Lyman, Paschen, Brackett, Fond and Humphreys. They were all calculated by Bohr's theory later on, but the similar type of equation you can use, the same constant, but here the first terminating cell, instead of 2 it is 1 square and x square, where the higher cells are 2, 3, 4 and so on. Similarly, Paschen series, the terminating cell is 3 instead of 2 here. Balmer it was 2, 3 here, and the higher cells are 4, 5, 6 and so on. Brackett it is 4, the terminating cell is 4 and the higher cells are 5, 6, 7. Similarly, in the Fond series, the terminating cell is 5 and the higher cells are 6, 7, 8. And in the Humphrey series, the latest series, this is 6 and the higher series are 7, 8, 9 and so on. So, before we close this session, a fundamental knowledge about atomic spectroscopy. We are not discussing about molecular spectroscopy, about other spectroscopies which are vast, but restricting to atomic spectroscopy, identification elements through their atoms in the vapor state. Those we have already done. Hopefully you have captured the right concept, the difference between the absorption and emission spectrum, the line spectrum and the continuous band spectrum. Last, I put a question to you. The question is like this: if you are taking sodium metal and its vapor, put a sodium metal in a flame, it will produce sodium vapor and it will produce the golden yellow flame. golden yellow light, you analyze that through prism, you get two lines D1 and D2. You understand, since sodium atom has one electron in the third level, you remember out of 11 electrons, 2 are in the K cell, 8 are in the M cell, and in the third cell there is only one electron, that is the valence electron. When it will absorb energy from that flame, it will be promoted to higher energy level. There are two levels about which we will not discuss now. And when they will return back from the two levels, they will produce two characteristic lines, D1 and D2 in the yellow region. Okay. But when you put, instead of sodium metal in the vapor, in the flame, sorry, you put sodium chloride crystal, common salt crystal in the flame, you also get the same golden yellow light and the same D1 D2 line. My question is, it was sodium atom, it is understandable. In sodium chloride, it contains sodium ion, Na plus ion. It doesn't contain that unpaired electron, that valence electron that was there in sodium atom. Now in sodium ion has a helium configuration. It has got 2 8. 8 is the octet, stable octet configuration. So that you will not lose any electron, it is stable. So where from the electron will come, and it will be excited, and when it will be de-excited, it will produce the golden yellow light. My question is, why sodium ion in sodium chloride is producing the same light? We are not talking about chloride or chlorine atom. The spectrum of chlorine doesn't fall in the visible region. Might be thinking that what about chlorine? Chlorine is a cipher here. I mean, has no role to play to give any spectrum in the visible region. It is the sodium which gives spectrum in the visible region. Not that chlorine doesn't give its spectrum. It gives in other region, but not in the visible. Now my question is, why Na plus will give the same spectrum while it doesn't have that valence electron that is there in sodium atom? Can you think of the reason? The reason I would like to share with you, I am trying to finish this lecture, this going little longer. Now this is like this. When you have sodium ion and chloride ion in a crystal and put it in flame, inside the flame this ionic bond breaks, no longer exists. The electron which was previously taken by chlorine atom to produce chloride ion will be returned back. The sodium ion will get back an electron from chloride ion. It will be converted to sodium atom in the flame and chlorine atom in the flame. There were 4 extra electron was now given back. So you forget about this. Now sodium atom is now present. So in the flame there is no ions. The ionic bond is all broken. It is converted to atoms, and then this will be promoted to 2 different higher energy levels, and when they return back to the same ground state, they will give you D1 and D2 lines. You understand? So in the flame, a sodium metal will give the same golden yellow light, same D1 D2 lines, whereas the sodium ion will also give the same lines, because in the flame there is no sodium ion. These sodium atoms are there. The ionic bond is broken. The electron gets transferred back again from chloride ion to sodium ion, producing atoms. So we can make a conclusion before we wind up, say goodbye. What we studied in atomic spectroscopy, we learned what is atomic spectroscopy. Each atom produces its characteristic spectral lines pattern, which is different from each other. For different atoms, different elements, the spectra are different. Atomic spectroscopy we learned. And we have 2 types of spectra. One is the continuous, and one is the discontinuous. This is called the band spectrum. This is called the line spectrum. Solar spectrum, Vibgyor, the sunlight from the spectrum obtained from the white sunlight, or black body radiation, or incandescent lamp. So these are continuous pattern. This is continuous spectrum. And discontinuous spectrum, you can be either lines, contains few lines, maybe in the absorption mode, or that is dark lines, or in the emission mode. Now spectra can also be divided into two types that we learned. One is emission spectrum. Emission spectrum, when a particular source is emitting radiation, whether it is emitting continuous radiation like sunlight or electric bulb, that it is a continuous emission spectrum, or it will be absorption spectrum. Absorption spectrum is always line, discontinuous. It is for elements only. The emission spectrum can be continuous or discontinuous. Solar, black body radiation, radiation from an electric bulb, incandescent electric bulb. So those are emission but continuous. But absorption spectrum of an element has to be line spectrum, and that too those are missing lines, dark lines. So when you take the help of a continuous light spectrum, allow it to fall on an element in the vapor state, in the cold state, and then analyze the residual light, you will find all the continuous pattern except those particular lines at which absorption has occurred. So that will give you the identity, the knowledge about the identity of that element. So, and also we learned about some little details about hydrogen spectrum, how hydrogen gas produces the light, which contains visible as well as invisible radiations, which when analyzed through prism to spectrum to spectrometer, they will produce 6 series of lines starting from Lyman to Humphreys, and each series has a very typical pattern. The gaps of lines will reduce towards the left, towards the lower wavelength region, and after few lines they will merge into one another to form a thin band called continuum. And the first series was discovered by Balmer, which is due to the series is due to the transition of electron from different higher levels to the second cell, 3 to 2, 4 to 2, 5 to 2, and so on. And then different series were discovered like Lyman, all transiting to the first cell, Paschen, all transiting to the third cell, the bracket, all transiting to the fourth cell, Fund, all transiting to the fifth cell, and the Humphreys, all transiting to the sixth cell. So with this we conclude this video lecture. Hopefully you have enjoyed my lecture, and we will meet once again in the third sequence of lecture in atomic structure for class 11. Thank you. Bye bye.